All right, welcome. Today we're diving deep into the world around us. I mean, really deep. We're going to zoom way, way in to figure out what everything you see, touch, and breathe is actually made of. So let's kick things off with a question that, you've probably known the answer to since you were a little kid. Why is it that you can build a sandcastle, but you can't build a water castle? I mean, have you ever tried? It just doesn't work, right? It's impossible. So what is the real difference here? Well, it really boils down to this one fundamental difference. You've got solids, like these stones here. You can pile them up, stack them, and they hold their shape. But then you have liquids, like this water, and they just flow. They take the shape of whatever you put them in. The secret to why that is, well, it's hiding at a scale that's totally invisible to us. Okay, so to crack this mystery, we've got to shrink ourselves down. I'm talking way, way, way down. Just imagine for a second, what if we could take something and just keep breaking it into smaller and smaller and even smaller pieces? Let's think about a simple piece of chalk, right? You can snap it in half, no problem. Then you can grind those pieces into a fine powder. But what if you could keep going? What if you could take 1 grain of that powder and split it, and then split it again and again? Eventually, you'd get to a point where you just can't go any smaller. You'd hit a wall. You'd be left with one single tiny speck of chalkness that is absolutely indivisible. And that tiny final speck, that's what scientists call a constituent particle. It's the absolute basic building block, not just of the chalk, but of, well, everything. And once you grasp this idea, that the entire world is built from these little bits, you're on your way to figuring out that whole sandcastle versus water castle thing. You see, this one single idea, this whole everything is made of particles thing, it's the master key. It's what unlocks our understanding of the 3 states of matter we see every day: solids, liquids, and gases. All right, first up, solids. And this metal key is a classic example, right? It's got a fixed shape, it's got a fixed volume, it's just a key. It's not going to change unless you, bend it or melt it. But why is it so stubborn? Well, if we zoom in again, we see the secret. Look at that. At the particle level, a solid is like a perfectly organized crystal. The particles are packed in super tight, locked into this rigid structure. They're like soldiers standing at attention. They can't march around. All they can do is kind of vibrate in place. And that's why solids are solid. This super tight, vibrating arrangement is what makes them rigid. All that order on the tiny, microscopic level adds up to give the big object we can actually see its fixed shape and volume. Okay, so that's solids. Now what about liquids? You look at the water in this picture, and it's totally different from the key. It flows, it sloshes around, it takes the shape of the pitcher. So what's going on with its particles? Yeah, when we zoom in here, things are a lot messier. The particles in a liquid are still pretty close together, but, and this is the key difference, they are not locked in place. They have enough wiggle room to slip and slide right past each other. It's kind of like people in a crowded room just milling about. And that freedom of movement, that ability to slide around, is exactly why a liquid can pour and take the shape of its container. But, and this is important, notice how they're still basically touching each other? That's why liquids have a fixed volume. A liter of water is a liter of water no matter what you pour it into. And that brings us to our third state, gases. Think about the air inside this balloon. You can't see it, obviously, but you know it's in there pushing out and filling up the whole space. Whoa, okay, now the particle view for a gas is a completely different ballgame. The particles are just gone wild. They're super far apart from each other, zipping around at incredible speeds, bouncing off the walls. It's mostly just empty space. And because they're so full of energy and so far apart, gases don't have a fixed shape or a fixed volume. They'll just keep expanding and expanding to fill up any container you put them in, no matter how big. So this brings up a really important question, doesn't it? If everything is made of these separate little particles, what's stopping them from just flying apart? Especially in solids and liquids, what holds them together? Turns out it's a kind of invisible glue. Scientists call this interparticle attraction, and you can totally think of it like that, like a tiny magnetic force that every particle has, pulling on all of its neighbors. It's this constant tug of war that tries to keep the whole group together. Now, in a solid, that attraction is super, super strong. It's what locks all those particles in place. But in a gas, the particles are so far apart and moving so fast, they barely even notice each other. That attraction force is basically negligible. It's almost zero.
Okay, but there's another piece to this puzzle. And funnily enough, it's not about what's there, it's about what isn't. I'm talking about the gaps, the empty spaces between all these particles.
Check this out. It's a really cool experiment. If you take a cup of water and stir in some sugar, something kind of weird happens. You'd think the water level would rise by the exact amount of sugar you added, right? But it doesn't. It rises by less. It's almost as if some of that sugar just vanished. So, what's the deal? We know the sugar didn't actually disappear. So where did it go? How can you add something to the water and not have the volume go up by the same amount?
The answer is just brilliant. The little sugar particles are so small, they don't just stack on top of the water particles. No, they actually fall into the empty spaces between the water particles. These gaps are called interparticle spaces.
And these spaces, these gaps, they also explain why you can compress some things and not others. It's super easy to push the plunger on a syringe full of air, right? That's because you're not actually squishing the air particles, you're just squeezing out all that empty space between them. But now, try doing that with a syringe full of water. Good luck. There are almost no gaps to close, so you can't really compress it at all.
Okay, we're almost there. There is just one last piece of the puzzle, and it's kind of mind-blowing. These particles, they are never still, not ever. They are in a constant, random, never-ending dance. Just look at this. You drop a crystal into a glass of water and watch what happens. The color spreads, all on its own, no stirring needed. This is you literally watching particle motion in action. The water particles are constantly moving, bumping into the crystal's particles and spreading them all through the glass. And by the way, this constant random motion, that's actually what temperature is. The hotter something gets, the faster its particles are dancing around. This whole never-ending dance is also the reason you can smell something, like perfume or baking cookies, from all the way across the room. The scent particles float into the air, and they get bumped and pushed around by all the moving air particles, carried along in this chaotic dance until they eventually reach your nose. So let's put it all together. It's really that simple. Everything we see, from a hard rock to the air we're breathing right now, it all comes down to a combination of these three things. As you move from a solid to a liquid to a gas, what's really happening? Well, the space between the particles gets bigger, that invisible glue holding them together gets weaker, and their movement goes from just a tiny vibration to an all-out, high-speed, chaotic dance. And that leaves us with one final thought to chew on. Think about it. The only real difference between solid ice, liquid water, and steam is just how much energy those little particles have and how they're arranged. So if that's true, what happens when we start messing with those forces on purpose? What happens when we supercharge that never-ending dance? Now that is where things get really interesting.